they'll hopefully be worthwhile to you. All right, this is just a picture straight off of the autonomic nervous system video by Hank Green with the crash course. And just to sort of remind you of how the nervous system works, I know the 232 people are now covering nervous system, the senses, cranial nerves, that kind of stuff. So hopefully that isn't completely foreign to you. Again, in the autonomic ganglia, which is sort of that halfway point between the spinal cord and brain, going to the two different branches of the autonomic nervous system, always it's acetylcholine binding nicotinic receptors. And once you get to the target organ, sympathetic nerves are releasing norepinephrine, and parasympathetic nerves are releasing acetylcholine binding muscarinic receptors. Now the nice thing is that although I covered about how there's M1, M2, M3, M4, M5 subtypes of muscarinic receptors, as of right now, there aren't any FDA-approved drugs, so you don't have to remember the different subtypes of muscarinic receptors yet. All right, so for all the different target organs, you can just remember all those target organs on the parasympathetic side have muscarinic receptors, acetylcholine receptors, and all the receptors on the sympathetic side are all alpha or beta adrenergic receptors. All right, so in the crash course video, they talked all about homeostasis and the idea that you have the two forces pushing against each other, the sympathetic nervous system and the parasympathetic nervous system. All right. Now, what I'm hoping to prove to you by the end of this lecture today is that if you memorized which of the sympathetic receptors are in which organs, and you know what the sympathetic nervous system does, that's why I made the fight or flight video. If you know those two things, then all you have to memorize for the test is the drug names. You won't have to memorize indications and contraindications because you already know them. I mean, you have to know them for the test, but you don't have to sit and just memorize them by rote because it should just make sense. So hopefully I can prove this to you over the course of an hour and 20 minutes. All right, so now here I have a thought experiment set up. And the idea is that I'm going to check heart rate in a test subject, and it could be a little rat, although their heart rate's going to be way faster. Or it can be me, it can be a person, doesn't matter. And the idea is I have a patient in one room, and I'm going to give them each one of these drugs, each time on a different day, so there's no interaction between them. And then I'm going to have a heart monitor, which is in a different room, that a different person is looking at, okay? So the first day, we're just going to measure the resting heart rate. And the resting heart rate in this situation is 80, and that's when the sympathetic and the parasympathetic nervous systems are at their resting state. They're both squirting out neurotransmitters on the heart, in this case, at a base level, which they just do all the time. All right, so that's the first day. Now, the second day, we're going to give a beta-1 agonist because beta-1 receptors are in the heart. All right, so we're going to give a beta-1 agonist, all right, and we have that same amount of parasympathetic tone that we had at rest. The parasympathetic system isn't doing anything differently, but we've added extra energy extra push power to the sympathetic side because now, in addition to having the resting amount of norepinephrine squirting out onto the heart, we've added that extra agonist. So the receptor is occupied more of the time, so there's more sympathetic tone, and so that drives the heart rate up. All right, so the person in the other room sees the heart rate has gone to 125. All right, the next day, all the drug is out of the system, and now this time we give a parasympathetic blocker. So the sympathetic side is at its normal resting tone in terms of how much is squirting out on the heart, but now we've made the parasympathetic side weaker because we blocked some of those acetylcholine receptors, those muscarinic acetylcholine receptors on the heart. And so now the sympathetic side drives the heart rate up because the parasympathetic side is weaker. All right? So the person in the other room sees the heart rate is 125. So does the person in the other room know if I gave a sympathetic agonist or a parasympathetic blocker? No, it doesn't. They don't know. Because a sympathetic agonist and a parasympathetic blocker will have the same visible effects on a target organ. The same measurable effects on a target organ, even though the drugs are binding completely different receptors, completely different nerves. This is a very unusual situation in the body. There's not a lot of situations where you have two things competing in this way. so perfectly. All right, so the next thing, let's just do the other experiment. This time, we're going to just give a parasympathetic agonist, a cholinergic drug that binds muscarinic receptors. And even though the sympathetic tone is its normal level, now the parasympathetic side drives the heart rate down because the parasympathetic side is boosted by that cholinergic agonist. And on our last day, we're going to give a beta-1 blocker, an anti-sympathetic, anti-adrenergic drug, which is that beta-1 blocker is going to bind the beta-1 receptors, block the effect of the sympathetic side. The parasympathetic side is just its normal self, but because the sympathetic side is weaker, it drives the heart rate down. So far, so good? All right, so what if I do this? All right, so sympathetic adrenergic agonist, antagonist or blocker, parasympathetic cholinergic side agonist or blocker, or anticholinergic antagonist. All right? All right, so when we give the sympathetic agonist, what happens to the heart rate? Increases, yeah? This pen stinks. And when we give the sympathetic blocker, the heart rate goes down. When I give a parasympathetic agonist, the heart rate goes down. And when I give a parasympathetic blocker, the heart rate goes up. All right, so do you see that there's a pattern here? This works for all of the autonomic things. It'll work for pupil, it'll work for urine flow, all of them. So sympathetic agonist, big pupil, dilated eyes. Sympathetic blocker, little pupil. Cholinergic agonist, little pupil. Anticholinergic drug, giant pupil. All right, works for urine flow. Do every single thing. Sympathetic agonist reduces urine flow. Sympathetic blocker increases urine flow. Parasympathetic agonist increases urine flow. Parasympathetic blocker or anticholinergic decreases urine flow. It works every time. So in terms of memorizing the effects of these 4 different classes of drugs, in fact, as a shortcut, you can say, well, I actually only have to know the effects of one of these 4. So if you can remember what the sympathetic nervous system does, then you know what all 4 classes of drugs do, because you can work it out. The parasympathetic side is always going to be the opposite. The antagonist and agonist sides will always be opposite, and you can always figure it out. So if I tell you there's an anticholinergic drug called atropine, does it give you dry mouth or does it make you drool? Right? So an anticholinergic, atropine, does that give you dry mouth or does it make you drool?
Dry mouth.
It gives you dry mouth, because the sympathetic side does too. So the key here is realize this is a mnemonic, but understand the underlying situation. You might say, well, why do I have to learn the underlying situation? I just remember this, I don't care about why. And the reason is that this side is binding cholinergic receptors and this side is binding adrenergic receptors. 2 totally different receptors. So when you're combining drugs, you're going to get kind of weird things happening. You know, if I just give a sympathetic agonist drug, like say I give it a beta-1 agonist, right? If I want the heart rate to get even faster, I mean, I could either give more of the original beta-1 agonist, I could give another beta-1 agonist, but it's going to bind the same receptors. But if I also give atropine, now the heart rate's going to just blow. It's just going to go huge high, because now what I've done is I've not only given an agonist to drive heart rate up, but I've also made this side weaker. So the heart rate will go way up. Whereas if I only just give more and more of the beta-1 agonist, there's a limit to how much I can do, because that parasympathetic side is still squirting out acetylcholine. Does that make sense? Right, so right now I've already reduced the amount of memorization, right, down to 1/4 of what it was when you walked in. Right? All right. Now I've made this little table for you. These drugs, the cholinergics and the adrenergics, have been around a long time. The first day I told you about atropine, this anticholinergic, belladonna, that makes people big. Adrenaline, epinephrine, norepinephrine are basically just adrenaline, right? So these sort of processes have been known about for hundreds and hundreds and hundreds of years, all right? Probably even before that, you know. And the reason, the problem with that is that whenever you have a system that's been around a long time, everybody gives it its own name. So the sympathetic agonists, you can call them sympathetic agonists or sympathomimetics, or you can call them adrenergics because they're binding an adrenaline receptor, or sympathetic agonists. But in clinical society, pretty much everyone refers to them as alpha agonist or beta agonist. And you're supposed to just know that in alpha and beta, you're specifically talking about adrenergic receptors. There's alpha and 1 subtypes of all kinds of receptors, but just when you're talking to another healthcare professional and you say, I'm giving this patient a beta agonist, they know you mean a beta adrenergic agonist. And similarly, for anti-adrenergics or sympathetic blockers, people refer to those as alpha blockers and beta blockers. Again, with the expectation that you know they're talking about alpha and beta adrenergic receptors. And same thing with the parasympathetic side. Parasympathetic is way too hard to say. Certainly nobody's going to say parasympathomimetic. That's way too hard to say. People just call those cholinergic drugs, or the blockers are called anticholinergics. Okay. In the fight or flight mnemonic video, there were 2 processes. I couldn't figure out a way to fit them into the sort of the metaphor of a young woman being chased through the forest by a monster. So 2 of them. One is renin-angiotensin-aldosterone, which is that system is activated by beta-1 receptors in the kidney. I don't really want to get into that until the 3rd exam because the people who are still taking 232 haven't covered that stuff yet. But it's part of it, and when we do the blood pressure drugs, that'll be very important. But for now, if it makes you nervous, don't worry about it right now. I won't ask you about it on the 1st exam, but if you know about it, that's extra happiness for you. And then the other thing is sexual function. So you have to have your sympathetic and your parasympathetic side working simultaneously in order to have good sexual function. And when I was in medical school, we had a kind of gross mnemonic, but I'll just share it with you because I think it's excellent. And the mnemonic is point and shoot. So point is erection and shoot is ejaculation. All right, so you need the parasympathetic side for erection, the sympathetic side for ejaculation, and for female orgasm you need the same. You need to have both. Right, so it's a weird thing. You have to be kind of relaxed and kind of excited simultaneously. So it kind of makes sense, right? You need both. So any drug that's going to block the parasympathetic or sympathetic side has the potential to screw up sexual function. And that's something that once you're working with patients and you get more and more practice talking to patients, you'll be able to ask them how their sexual function is in a way that's not threatening or embarrassing. That takes a little bit of practice, but that'll come there. So I think on the different tables where I say different effects of the different drugs, if it's a blocker of either side, there's sexual function problems. So I kind of don't just repeat it over and over again. Okay, some terms you should already know. This is a little smaller. Vasoconstriction and vasodilation. Vasodilation means vaso is blood vessel, dilation means widening. Vasoconstriction is blood vessel constriction, narrowing. So vasodilation and vasoconstriction specifically refers to blood vessels. That can be arteries or veins. Don't get that confused with bronchodilation or bronchoconstriction, which is the widening or constricting of the air passages. That's a different thing. All right. Now, here's sort of a horrible picture. I'm not going to ask you to draw diagrams of these different molecules, but just notice that epinephrine, norepinephrine, and dopamine, they all look pretty similar. So it probably shouldn't be that surprising that epinephrine and norepinephrine bind the same kind of receptors because they're the same shape. Does that make sense? What I'm trying to show you in this picture, this is just the production of norepinephrine at the nerve terminal, right? And you start out with tyrosine, it becomes dopa, then it turns into dopamine, then is turned into norepinephrine, which is then packaged into vesicles, and then the vesicles open up at the cell membranes and norepinephrine is released. It binds the receptor and bounces out a few times, and then it diffuses away, where it either gets broken down by an enzyme like COMT or MAO, or it gets sucked back up and reused, or it gets sucked up and broken down, or sometimes it actually can bind other things and it'll stop the whole process. The reason I'm showing you this is not because I want you to draw that picture for me, but because I want you to understand there's all different ways we can mimic or block any body system. You don't just have to mimic or block a ligand by binding its receptor. You can also mimic or block it by changing the levels of the ligand itself. So when we talk about direct acting drugs, those are drugs that are binding the receptor itself and either activating the receptor or blocking it. All the other kind of ways that you interfere with this are the indirect acting drugs. So if I want to make more norepinephrine and increase heart rate in the heart, I can do it a couple different ways. I can somehow drive this system forward. I can increase how many vesicles are opened up and released at the nerve terminal. I can inhibit the enzymes that break it down, right? So there's all different ways that I can do that, and that's indirect. That's an indirect acting drug. So this, we're gonna come back to this picture over and over again through the semester because this chemical process is quite important in lots of cases. But the thing to get here is this idea of direct acting and indirect acting. In a direct acting drug, you're using an agonist or a blocker. In an indirect acting drug, you're changing the actual levels of the natural ligand itself. So for this case, we would be talking about norepinephrine, or in the case of parasympathetics, acetylcholine. All right? Okay, so you've already seen this table, all right? And what's great about this is if you've already memorized this table, again, you're going to be able to predict indications and side effects for drugs. So for instance, if I have a drug that I'm going to use to dry out my sinuses, right? Alpha-1 receptors constrict non-essential blood vessels, including the ones in your sinuses. And when the blood vessel is constricted, it doesn't leak as much, which is why an alpha-1 drug will help a runny nose. Because if the blood vessels in your sinuses are nice and tight, they won't leak fluid. But you might say, okay, I'm going to have a drug that's an alpha-1 agonist that I'm going to use so that my nose doesn't run. All right, well, it should first of all make sense that that would be one of its indications. Runny nose is the indication for alpha-1. And I say, well, here's an alpha-1 drug. What else do you think it does? You could say, you could sit and try to memorize what it does, or you could say, well, it's alpha-1, so it must constrict non-essential blood vessels and increase blood pressure. It must dilate pupils. It must give people a dry mouth and make them constipated. It probably reduces their the flow of urine, makes it the flow of urine is lower. And you would be right. Those are different indications you could use for an alpha-1 agonist. And then I say, well, what's the side effects? Well, the side effects are going to be they dilate your pupils, they increase your blood pressure, they make you constipated, they make your urine flow lower. That's the side effects. So without even knowing a single drug name, you already know the indications and the side effects of the different drugs. Now in clinical practice, there are different alpha-1 agonists that are used for different things because we've just over time discovered that those drugs seem to work better for certain things than others. Because there's, I didn't mention this before, but there's not only alpha and beta, alpha-1 and beta-1 and beta-2 receptors, there's also alpha-1, there's alpha-1A receptors, and there's alpha-1B receptors, and so forth, right? But this is an introductory course. Let's stay on an introductory level and just say that for right now, I'm more interested in learning the classes of the drugs. So if you just think alpha-1 agonist is going to do this stuff, you're in good shape. Beta-1, again, I don't want to talk too much about kidney, but beta-1 receptors are in the heart and kidney. So a beta-1 receptor, a beta-1 agonist is going to increase heart rate. So what's the indication for a beta-1 agonist? Well, why would you use something that increases heart rate? Because your heart rate was too low, right? Yeah? All right, so you know that one. Beta-2, there's receptors in the lungs, uterus, and major skeletal arteries, right? So let's examine the half of the population who does not have a uterus, and say, okay, what indication would you use a beta-2 agonist for?
Asthma.
Use it for asthma or any kind of breathing problem, right? Because it makes it easier to breathe. Do you think there's a big market for beta-2 blockers? Yeah? Because when would you want to make a patient unable to breathe? Never. No, that's not going to be something you want to do. And you might say, well, maybe you want to use some kind of beta blocker to make your uterus contract more. Well, I mean, you could. There's a lot of better drugs for that. And the side effect is it'll make it really difficult for the patient to breathe. That's a side effect you don't want to deal with. All right? So, well, here's the side effect. All right, so here's something maybe you can help me explain. If you take a beta-2 agonist for your asthma, a very common side effect in that is palpitations, rapid heartbeat. So how can that be? I take a beta-2 agonist, and get a rapid heartbeat. So the way to figure it out is to say, well, what else does it do? So again, let's do it in a phenotypic male who does not have a uterus. And we've given them this drug for their asthma. They can breathe pretty easy, but their heart is pounding. Well, what else? Where else are beta-2 receptors? Yeah.
Since the arteries are dilated, it's going to have to pump his heart faster to get more blood.
Exactly. Right. So the blood vessels in the legs and the major essential vessels dilate. Whenever you get dilation of blood vessels, you get the blood pressure goes down, and then your body tries to compensate for that by what's called reflex tachycardia. The reflex of your body is to increase your heart rate. So it makes sense. You can memorize it too, but you can also, it also makes sense. If you're ever sitting and looking at it, I mean, one thing I frequently put on tests is I put in a made-up drug. I say, here's a made-up drug. It's a beta-2 agonist. What are going to be the side effects? If you haven't memorized, if you just memorize drug names, you're out of luck there. You have to understand what the drug class does. All right? There's also beta-3 receptors and alpha-2 receptors, and I don't want to deal with those. We'll deal with those later. All right? So again, the adverse or side effects are due to the activation of receptors on different organs. Now, I mentioned already cholinergic drugs. All these autonomic nerves, all these autonomic target organs all have muscarinic receptors on them. So pretty much anytime you activate or block a muscarinic receptor, you get all the side effects because there's not that differentiation between the different organs. So that makes it easier in terms of learning it, but not as good in terms of using them as a drug because it's so nonspecific.
Can you just repeat that real fast?
Sure. What did I just say?
About. Just that if you block the muscarinic.
Right. So if you have, right. So if you've got, right. So we have, the eye, and we have the heart, and we have the lungs, right, and we have blood vessels and such things like that. In the eye, you have alpha-1 receptors. In the heart, you have beta-1. In the lungs, you have beta-2. In the blood vessels, in the non-essential ones, you have alpha-1. In the essential ones, you have beta-2, right? So you kind of have to, you can target different drugs to different systems based on what receptors in that system, okay? But on the cholinergic side, it's all muscarinic, right? So if I give a muscarinic agonist, it's going to give you a small pupil. It's also going to slow your heart rate, make it tough to breathe, and do the opposite on the blood vessels. Does that make sense? Yeah. It just makes it a lot easier to memorize, but it makes it a crappier class of drugs because it's not specific.
Because with the adrenergic, it goes to a specific, it goes to the heart, it goes to...
It'll only bind the receptors that when we develop a drug that's a specific beta-1 agonist, okay. The hope is that when you give the drug, it's only going to bind beta-1 receptors and leave the other target organs alone. Okay. Because the idea is that, say we have a beta-1 agonist, it's floating around your bloodstream, sort of throughout your whole body, and then when it goes past the heart, past the right atrium, there's receptors with a catcher's mitt waiting for it to float by and then be activated and have its effect on the heart. Does that make sense? All right. this is just this idea of reflex tachycardia, reflex bradycardia. I'm going to ask you to look at the dog lab video, and there's a handout. And I would advise you not to do that until you've studied everything else, because it's way easier if you understand and sort of have all this other stuff memorized. But the trick to those questions is always going to be, figure out what the blood pressure is with the drugs, and then figure out what the reflex is going to be. So figure out what the drug does in terms of blood pressure. If the blood pressure goes up, your heart is going to slow down. If the blood pressure goes down, your heart's going to want to increase. So you can block that reflex different ways, but you always figure out first figure out the blood pressure, then figure out the reflex. Okay. And also don't get confused. I mentioned the vagus nerve here because the vagus nerve is the cranial nerve that carries the acetylcholine, the parasympathetic fibers to the heart. Unfortunately, the sympathetic fibers to the heart form this like weird plexus of net of nerves, and so it doesn't have a name. So, I mean, we could just ourselves just start calling it Steve or something. Say, okay, the Steve nerve then stimulates the heart to increase heart rate through beta-1 receptors. The vagus nerve only reduces heart rate through binding the cholinergic muscarinic receptors. So don't get confused if the vagus nerve does both of those things. It doesn't. It only mediates the parasympathetic response. Okay, I'm actually going to press forward, but if you need to take a water break or a bathroom break or just I can't take it anymore, I need a break, that's what we're going to do. I'm just going to talk about some of these drugs, and that's my